What if the entire universe, every galaxy, every star, every atom in your body, was once squeezed into a space smaller than a single grain of sand? It sounds like science fiction, but this is the staggering reality behind the Big Bang, the moment everything began. Think about that for a second. The vast expanse of space, with its billions of galaxies stretching farther than we can fathom, all traces back to an unimaginably tiny point of pure energy and potential. How does something so infinitely small become everything we know? That's the mystery we're about to unravel. For centuries, humans have looked up at the night sky and wondered where it all came from. Ancient civilizations told stories of gods and giants shaping the cosmos, but today we have something even more extraordinary: science. The Big Bang Theory isn't just a story, it's our best understanding of how the universe exploded into existence, transforming from a seething, chaotic furnace into the ordered beauty we see today. Yet, for all we've discovered, there are still layers of this cosmic saga waiting to be uncovered. What really happened in those first fleeting moments? How did randomness give way to the precise laws that govern our reality? And what secrets are still hidden in the echoes of that primordial explosion? This is the untold story of the Big Bang, a journey from chaos to cosmos. We're going to travel back to the very beginning, to a time before time, when the universe was a swirling maelstrom of energy and possibility. Along the way, we'll confront mind-bending questions, challenge long-held assumptions, and uncover the hidden forces that shaped everything from the tiniest particles to the grandest galaxies. By the end, you'll see the universe and your place in it in a whole new light. So buckle up. We're about to embark on the greatest adventure of all, the story of how everything came to be. The singularity is where our story truly begins, a point so unimaginably small that it defies logic. Picture this: all the matter and energy that would one day become galaxies, stars, and even you, compressed into a space smaller than an atom. It wasn't just dense, it was infinite density, a state where the laws of physics as we know them simply break down. Here's the paradox: how could everything emerge from what appears to be nothing? That nothingness wasn't empty, it was a seething, unstable sea of potential, where gravity, space, and time didn't yet exist in any recognizable form. Einstein's theory of relativity gives us clues, suggesting that under such extreme conditions, matter and energy become indistinguishable. Yet, when we try to apply quantum mechanics, the rules governing the smallest particles, the math collapses into chaos. This is the great scientific tug of war. Relativity paints the singularity as a definitive starting point, while quantum theory hints that nothing might be far more complicated. Some physicists speculate that the singularity wasn't an absolute beginning, but a rebound, a cosmic bounce from a previous universe that had collapsed in on itself. Could our Big Bang have been just one heartbeat in an endless cycle of expansion and contraction? The closer we look, the more elusive the singularity becomes. It's like staring into a hall of mirrors. Every answer raises new questions. But one thing is certain: from this incomprehensible state emerged the spark that ignited everything. In the next instant, the universe would erupt into being, setting in motion the chain of events that forged reality itself. What unleashed that cataclysmic moment? That's where the story gets even more astonishing. The Planck epoch is where the universe becomes unrecognizable, a realm so alien that even our most advanced physics falters. Picture this: in the first 10 million trillionth of a second after the Big Bang, temperatures soared beyond comprehension, hitting values so high that numbers fail to convey their enormity. At this scale, the four fundamental forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, were fused into a single, unified superforce. There was no matter as we understand it, no particles, no space or time in any familiar sense. Instead, the cosmos was a seething, churning ocean of raw energy, where the very fabric of reality fluctuated wildly. To grasp just how extreme this environment was, imagine taking all the energy in today's observable universe and cramming it into a space smaller than a single atom. The density would be so intense that gravity itself would become as powerful as the other forces, warping the quantum foam of space-time into shapes beyond our imagination. Under these conditions, the universe didn't just behave differently, it followed rules we're still struggling to decode. Some theories suggest that at this scale, space and time might have been granular, like the pixels on a screen, or that multiple dimensions beyond our familiar four flickered in and out of existence. Then something extraordinary happened. In a fleeting moment, the universe underwent a growth spurt so rapid it defies intuition: cosmic inflation. Think of it like a balloon inflating faster than the speed of light, stretching a subatomic speck into something the size of a grapefruit in less than a blink. This wasn't just expansion, it was exponential, smoothing out the primordial chaos into a nearly uniform sea of energy. Yet, hidden in that smoothness were tiny quantum ripples, imperfections so minute they'd go unnoticed for billions of years. These microscopic wrinkles would one day become the seeds of galaxies, the cosmic blueprint for everything from galaxy clusters to the voids between them. How? Because in those infinitesimal fluctuations, gravity had something to grip. Slightly denser regions where matter would eventually gather, drawn together by its own pull. This is the paradox of inflation. It made the universe incredibly uniform while simultaneously planting the subtle variations that gave rise to structure. Without those quantum whispers, the cosmos might have remained a featureless expanse, devoid of stars, planets, or life. Yet here's the puzzle: what triggered inflation in the first place? Was it an inevitable phase transition, like water freezing into ice, or the result of some deeper, still hidden mechanism? The answers might lie in a theory that unites quantum mechanics and gravity, a holy grail of physics that continues to elude us. One thing is certain: in that first fraction of a second, the universe set in motion everything that would follow, from the first atoms to the sprawling cosmic web we see today. And somehow, against all odds, those primordial conditions were precisely tuned to make our existence possible. Cosmic inflation wasn't just a phase, it was the universe's most extreme makeover. Imagine a balloon inflating so rapidly that every tiny wrinkle on its surface stretches out until it's nearly invisible. That's what happened to our cosmos in less than a trillionth of a second. Before this revelation, scientists were puzzled by two baffling observations: the horizon problem and the flatness of the universe. The horizon problem asked why distant regions of space, seemingly never in contact, had identical temperatures. Without inflation, these areas wouldn't have had time to exchange heat, like two strangers on opposite sides of the planet wearing the exact same outfit. Inflation solved this by stretching a once tiny, uniform region across the entire observable universe, preserving that thermal harmony. Then there's flatness. The universe's geometry is so finely balanced between expansion and collapse that it defies chance. Picture a pencil perfectly balanced on its tip, an unstable equilibrium that should have toppled long ago. Inflation smoothed spacetime into this improbable flatness by stretching any initial curvature until it became negligible, like blowing up a crumpled sheet of paper to the size of a galaxy. These breakthroughs shattered the earlier steady-state theory, which imagined a universe eternally expanding but always looking the same, a concept that couldn't explain the searing heat of the Big Bang's afterglow or the abundance of light elements. The architect of this cosmic revolution, physicist Alan Guth, who in 1980 proposed inflation as a happy accident of quantum fluctuations. His work revealed how a bizarre, high-energy state called a false vacuum could unleash repulsive gravity, driving exponential expansion, yet mysteries linger. What ended inflation? Some theorize it was a quantum collapse, like a bubble popping in a boiling pot, releasing the energy that forged the first particles. Others suggest multiple bubble universes formed, each with its own physics. What's undeniable is inflation's legacy. Those quantum ripples it amplified became the scaffolding for galaxies. Without them, gravity would have had nothing to grasp, leaving the universe a dark, empty void. So when you gaze at the night sky, you're seeing the echoes of that explosive growth, a fleeting moment that set the stage for everything to come. But how did raw energy transform into the atoms that make up our world? That's where the story takes an even more remarkable turn. As the universe expanded and cooled from its unimaginably hot infancy, it entered a phase stranger than any science fiction, a seething ocean of quark-gluon plasma. Picture a cauldron so energetic that particles couldn't even hold themselves together. Quarks, the building blocks of protons and neutrons, danced freely alongside their antimatter counterparts, constantly colliding and annihilating in bursts of pure energy. For every particle created, an antiparticle emerged, locked in a deadly tango of mutual destruction. Under normal circumstances, this symmetry should have left the universe barren, a void with no matter at all. Yet here we are, in a cosmos teeming with galaxies, planets, and life. How did matter win this cosmic duel? The answer lies in a tiny, mysterious flaw in the universe's blueprint. In 1967, physicist Andrei Sakharov proposed three radical conditions that could explain our matter-dominated reality. First, the universe had to be out of thermal equilibrium, a state where particles could behave differently from their antiparticles. Second, there needed to be a process called charge parity violation, where matter and antimatter don't perfectly mirror each other. And third, these interactions had to occur at a time when the universe was still hot enough for particles to transform. Think of it like baking a cake slightly lopsided. If the conditions are just off balance, you end up with more batter than crumbs. The kicker, we've actually observed CP violation in action. In experiments with particles called kaons and B mesons, scientists watched as matter decayed at a different rate than antimatter. The difference was minuscule, just one extra particle in every 10 billion. But in the furnace of the early universe, that tiny bias was enough to tip the scales. The hunt for deeper clues continues inside colossal machines like the Large Hadron Collider, where physicists recreate quark-gluon plasma to study its secrets. Some theories suggest even more exotic possibilities, that hidden particles like neutrinos might hold the key, or that the imbalance originated during inflation itself. What's clear is that this primordial asymmetry wasn't just a quirk. It was the universe's first lottery win, a 1 in a billion fluke that made atoms and us possible. And then the temperature dropped just enough for quarks to finally slow down and stick together. Protons and neutrons began to form, setting the stage for the next act, the birth of the first atomic nuclei. But that transformation wouldn't be smooth. The universe was about to enter its most fragile phase, a delicate dance between creation and annihilation that would determine whether light or darkness ruled the cosmos. For 380,000 years, the universe was a swirling fog of charged particles so dense that light couldn't travel more than a fraction of an inch before being absorbed and re-emitted. Picture trying to see through a blizzard at night, where every snowflake scatters the beam of your flashlight. That's how trapped photons were in this primordial plasma, endlessly bouncing between free electrons and nuclei. But then, the temperature of the cosmos dropped below 3,000 degrees, a threshold that changed everything. Electrons, no longer energized enough to resist the pull of atomic nuclei, began to pair up with protons, forming the first stable hydrogen atoms. This moment, known as recombination, didn't just create matter as we know it, it set light free. Photons that had been bouncing around for eons suddenly had a clear path, streaming outward in all directions. In an instant, the universe transformed from opaque to transparent, and those liberated photons became what we now call the cosmic microwave background. It's like the flash from a cosmic camera freezing the infant universe in a single frame. Here's the astonishing part: that faint glow isn't just a relic, it's everywhere. Tune an old analog television to a dead channel, and about 1% of the static you see is this ancient light, stretched and cooled by 14 billion years of cosmic expansion. But the CMB isn't uniform. Tiny variations in temperature, differences of just millionths of a degree, reveal where matter was slightly denser or sparser in those early moments. These fluctuations are the fingerprints of quantum ripples from inflation, the seeds that gravity would later sculpt into galaxies and voids. Scientists have mapped these patterns with satellites like Decode and Planck, creating ultra-precise baby pictures of the cosmos. The data reveals startling clues. The universe is geometrically flat to within a fraction of a percent, and ordinary matter makes up less than 5% of its total content. The rest, dark matter and dark energy, two mysteries we're still unraveling. Even more intriguing, the CMB's polarization patterns hint at gravitational waves from inflation itself, potentially offering a glimpse into the universe's first trillionth of a second. What makes this glow so revolutionary is its permanence. Long after the last stars burn out, the CMB will still be there, a fading echo of creation. And buried in its subtle patterns are answers to questions we haven't even thought to ask yet about the nature of time, the shape of space-time, and whether our universe is just one bubble in an infinite cosmic foam. Those faint whispers of heat in the cosmic microwave background aren't just random static, they're the universe's first love letter, written in the language of temperature. Imagine looking at a black and white map where every barely perceptible shade of gray tells an epic story. That's what scientists found when they analyzed the CMB's anisotropies, those minuscule fluctuations as small as 1 part in 100,000. A patch slightly warmer here meant atoms were packed a little tighter. A cooler spot there hinted at a void waiting to form. These imperfections were the genetic code for everything to come, the gravitational footholds that would one day pull matter into galaxies. The real magic lies in how these microscopic ripples became cosmic mountains. Picture dropping a single grain of sand into a still pond. The tiny splash creates ripples that grow as they spread. In the early universe, gravity played that amplifying role. Slightly denser regions pulled in more matter, which increased their gravitational pull, attracting even more material in a snowball effect spanning billions of years. What began as quantum whispers during inflation became the scaffolding for superclusters, colossal threads of galaxies stretching across the void like foam on an ocean wave. We owe this understanding to missions like Decode and Planck, which turned the CMB from a fuzzy glow into a high-definition cosmic fingerprint. Decode's first detection in 1992 was so monumental that lead researcher George Smoot compared it to seeing the face of God. Then came Planck with resolution so sharp it could spot variations a third the size of the Moon from Earth. These satellites didn't just confirm the Big Bang, they revealed its granular texture, showing how specific density patterns matched predictions down to the decimal point. Yet the CMB still guards profound mysteries. Why do certain large-scale fluctuations defy expectations? Could odd alignments in the data hint at a universe far stranger than we've imagined? Each answer peels back another layer, showing how those primordial temperature differences didn't just build galaxies, they encoded the universe's fate. Now, as we trace the journey from those initial ripples to the cosmic web, we're left wondering what other secrets are written in that ancient light waiting to be decoded. After the cosmic microwave background faded into the darkness, the universe entered its most mysterious chapter, a silent era stretching for millions of years where not a single star flickered in the void. Imagine a cosmos so pitch black that if you'd been there, your eyes would have seen nothing, no matter how long they adjusted. This was the cosmic dark ages, a time when the universe was little more than an endless sea of hydrogen gas, so thick it swallowed every trace of light. The reason for this all-consuming darkness lies in the physics of hydrogen atoms. As the universe cooled, these atoms settled into their lowest energy state, absorbing any stray photons that dared to pass through them. It was like trying to shine a flashlight through wet paper. Light simply couldn't escape, but hidden within this gloom were the quiet stirrings of structure. Tiny density variations from the primordial plasma, now frozen into the CMB, began pulling hydrogen together under gravity's relentless tug. Vast, diffuse clouds started forming proto-galactic halos, invisible giants waiting for their moment to ignite. The key to unlocking this shadowy epoch might lie in an unlikely place: radio waves. Neutral hydrogen emits a faint signal at a wavelength of 21 centimeters, a whisper from the dark ages that could map the universe before stars. Projects like the Square Kilometre Array aim to catch these echoes, peeling back time to reveal how matter clumped before the first galaxies. It's like tuning a cosmic radio to a station 14 billion years old, searching for static that holds the blueprint for everything. Then, around 200 million years after the Big Bang, everything changed. Somewhere in the depths of those hydrogen clouds, gravity's pressure grew too intense. Atoms collided, temperatures soared, and in a flash of nuclear fusion, the first star blazed to life. This was cosmic dawn, the moment light finally tore through the darkness, ending the universe's longest night. But these weren't the gentle stars we know today. They were monsters, hundreds of times more massive than our sun, burning ferociously and dying young in titanic explosions that seeded the cosmos with heavier elements. What's astonishing is how fragile this transition was. Had hydrogen been just slightly more efficient at absorbing light, or gravity a fraction weaker, the dark ages might have stretched on indefinitely, a universe forever trapped in shadow. Instead, those first stars became beacons, their ultraviolet radiation stripping electrons from surrounding hydrogen in a process called reionization. Slowly, the fog lifted, and the universe became transparent once more, setting the stage for galaxies to assemble. We're only beginning to piece together this hidden era, but one thing is certain: without those first, fragile sparks, the cosmos as we know it would never have emerged from the dark. The first stars didn't just light up the universe, they rewrote the rules of cosmic chemistry. Born from pristine clouds of hydrogen and helium untouched by previous generations, these celestial titans, called Population 3 stars, were unlike anything that exists today. With no heavier elements to help them cool and fragment, they grew to staggering sizes, some reaching masses hundreds of times that of our sun. Imagine a furnace so colossal that its core burned at temperatures over 100,000 degrees, fusing atoms at a rate that would make modern stars seem like flickering candles. Their pure composition made them both spectacular and short-lived. Without carbon, oxygen, or other elements that help regulate nuclear reactions in today's stars, these behemoths burned through their fuel in mere millions of years, a cosmic blink compared to our Sun's 10-billion-year lifespan. But their deaths were even more consequential than their births. When these stars finally collapsed under their own weight, they didn't fade quietly. They detonated in supernovae so violent they briefly outshone entire galaxies. These explosions were the universe's first alchemists. In their searing aftermath, temperatures and pressures reached levels never before seen, forging elements like carbon, oxygen, and iron in their cores. For the first time, heavier atoms, the building blocks of planets and life, were scattered across space. This stellar dust became the raw material for future generations of stars, including population 2 and eventually population 1 stars like our Sun. What's truly remarkable is how finely tuned this process was. Had those first supernovae been slightly less energetic, heavier elements might have remained locked in stellar cores forever. A bit more violent, and the delicate balance needed for complex chemistry could have been disrupted. Yet somehow, against astronomical odds, these early stars struck precisely the right note, a cosmic symphony of destruction and creation that set the stage for everything to come. Now picture this: every atom in your body heavier than hydrogen was once forged in the heart of a star. The calcium in your bones, the iron in your blood, even the gold in your jewelry, all were born in these primordial furnaces or their cataclysmic deaths. That means we're not just observers of the cosmos, but literal stardust given consciousness, tracing our lineage back to those first, magnificent monsters of light. The universe was no longer a shapeless sea of gas gravities invisible, and began sculpting the chaos into something extraordinary. Picture trillions of tons of hydrogen and dark matter swirling in an intricate ballet, drawn together by an unseen choreographer. This was the birth of galaxies, a process so slow it makes mountain ranges seem fleeting. But what's truly mind-bending is that most of the mass pulling everything together wasn't even visible. Dark matter, mysterious, intangible, yet outweighing ordinary matter 5-to-1, formed vast, ghostly scaffolds around which galaxies would grow. Modern supercomputer simulations like Illustrious let us witness this cosmic drama unfold. They reveal a universe threaded with delicate filaments of gas and dark matter, a sprawling cosmic web where intersections became the nurseries of galaxies. Like rivers feeding lakes, these filaments channeled raw material into hungry protogalaxies. The simulations match stunningly with real observations. Telescopes like Hubble and JWST spot these same tendrils stretching across the void, illuminated by the glow of newborn stars. Our own Milky Way has a history written in collisions. Billions of years ago, it likely swallowed smaller galaxies, their stars strewn across our halo like fossils. One such victim, Gaia Enceladus, left its mark in the unusual orbits of stars we see today. And we're not done yet. The Milky Way is on a collision course with Andromeda, a slow-motion crash that will reshape both galaxies in about 4 billion years. But there's another invisible player in this story: supermassive black holes. Lurking in galactic cores, these monsters weigh millions of suns and wield surprising influence. When they feed, they unleash torrents of energy that can heat surrounding gas, stifling star formation, or in some cases, trigger it. They're the universe's paradoxical architects, capable of both creation and destruction on scales we're only beginning to understand. The dance of galaxies isn't just about gravity. It's a story written in light, dark matter, and the unimaginable power of black holes. If you could travel back to the universe's chaotic youth, you'd witness a spectacle unlike anything in today's skies: quasars, the most luminous objects in existence. These brilliant beacons outshine entire galaxies, blazing with the energy of 1 trillion suns packed into a region no larger than our solar system. At their heart lies a voracious supermassive black hole, feeding on gas and stars at such a staggering rate that it creates an accretion disk hotter than the core of any star. The friction within this swirling maelstrom generates blinding radiation across the spectrum, from X-rays to radio waves, visible clear across the cosmos. What makes quasars so extraordinary is their role as cosmic time capsules. Because light takes time to reach us, the most distant quasars we observe are snapshots of the universe when it was less than 1 billion years old. They reveal a time when galaxies were raw and violent, their central black holes growing at breakneck speed. The brightest quasars emit enough energy in 1 second to power human civilization for millions of years, a testament to the raw power lurking in the early universe. But quasars weren't just cosmic show-offs, they were the universe's great sculptors. Their intense radiation acted like ultraviolet blowtorches, stripping electrons from hydrogen atoms in a process called reionization. This crucial epoch, ending the cosmic dark ages, made the universe transparent to light again, allowing galaxies to shine unobstructed across the void. Without quasars, the fog of neutral hydrogen might have persisted far longer, delaying the formation of stars and planets as we know them. Interestingly, quasars also betray their own eventual fate. As black holes consume the surrounding gas, their fuel supply dwindles and the dazzling accretion disk fades. What remains is the quieter, but no less fascinating active galactic nucleus we see in galaxies like our own. This transition hints at a universal cycle of feast and famine, where even the mightiest cosmic engines must eventually slow. Yet quasars are just one chapter in the story of cosmic evolution. Beyond their brilliance lurked even more extreme phenomena: gamma-ray bursts, hypernova, and collisions between neutron stars, each unleashing forces that further shape the chemistry and structure of the universe. These titanic events didn't just light up the cosmos, they forged the very elements that would one day become planets, oceans, and life itself. The early universe was a crucible of transformation, where destruction and creation danced in perfect balance. Among all the cosmic mysteries we've uncovered, none is more baffling than dark matter, the invisible hand shaping the universe. Picture a merry-go-round spinning so fast that its outer horses should fly off, yet somehow they stay firmly in place. That's exactly what astronomers observed in galaxies, stars orbiting so rapidly that visible matter alone couldn't explain their motion. The math was undeniable: some unseen mass, outweighing ordinary matter 5 to 1, must be holding these galaxies together with its gravitational grip. But the evidence doesn't stop there. When astronomers train their telescopes on massive galaxy clusters, they notice something extraordinary. Light from distant galaxies bends as it passes through, as if the cluster were a giant lens. This gravitational lensing reveals an astonishing mismatch. The visible matter accounts for only a sliver of the bending power. The rest comes from vast, diffuse halos of dark matter enveloping the clusters like ghostly cocoons. Perhaps the most striking proof came from the Bullet Cluster, a cosmic collision where two galaxy clusters smashed through each other. X-ray telescopes caught ordinary matter superheated gas, slowing down and pooling at the collision site, while gravitational lensing showed the bulk of the mass had sailed right through, barely interacting. It was as if two crowds of people collided, but their shadows kept walking undisturbed. This proved dark matter isn't just an anomaly, it's something fundamentally different, a substance that barely notices the universe we know. For decades, scientists have hunted for dark matter particles, constructing detectors deep underground to shield them from cosmic noise. Theories pointed to WIMP, weakly interacting massive particles, that might reveal themselves through rare collisions with ordinary atoms. Yet after exhaustive searches, from Italy's Gran Sasso lab to Antarctica's ice cube, no definitive signal has emerged. Alternative candidates like actions hypothetical particles born from quantum field theory are now in the spotlight, with experiments like ADMX tuning into frequencies where these elusive particles might ring. The deeper we dig, the stranger the possibilities become. Could dark matter be a family of particles as complex as the visible matter we know? Some theories suggest entire dark sectors with their own forces and interactions hidden in plain sight. Others propose that we've misunderstood gravity itself, that Einstein's equations need revising on cosmic scales. But just as we grapple with dark matter's secrets, an even more perplexing force emerges: dark energy, pushing the universe apart at an accelerating rate. Together, these two invisible components make up 95% of reality, leaving us with a humbling truth: we've only begun to map the cosmos's true architecture. The universe, it seems, is far stranger than we ever imagined. Just when cosmologists thought they understood the universe's fate, a discovery shattered the prevailing wisdom. In 1998, two independent teams studying distant supernova made an observation so shocking it earned them the Nobel Prize. The universe wasn't just expanding, it was accelerating. Like a car pressing harder on the gas pedal as it speeds away, galaxies were racing apart faster over time, defying expectations that gravity should be slowing everything down. The culprit, a mysterious repulsive force dubbed dark energy, now known to make up a staggering 68% of the cosmos. Here's what makes dark energy so baffling. Unlike gravity, which pulls matter together, dark energy behaves like an anti-gravity agent, pushing space-time apart from within. On cosmic scales, its influence is relentless as the universe expands. Dark energy's grip strengthens because it's tied to space itself. The more space stretches, the more dark energy emerges, creating a feedback loop that could leave galaxies isolated in an ever-growing void. Imagine blowing up a balloon with dots on its surface. At first, the dots drift apart slowly, but as the balloon inflates faster, the dots race away until they can no longer see each other. That's the fate dark energy might impose on our universe. Einstein actually predicted something like this a century ago with his cosmological constant, a mathematical fix he later called his greatest blunder, when Edwin Hubble proved the universe was expanding. Ironically, modern observations suggest Einstein might have been right after all. The cosmological constant fits the data beautifully, portraying dark energy as a uniform, unchanging force woven into spacetime's fabric. But alternative theories argue dark energy could be dynamic, a fluctuating quantum field nicknamed quintessence that might weaken or strengthen over time. The implications are staggering. If dark energy intensifies, it could eventually tear apart galaxies, stars, and even atoms in a catastrophic big rip. Alternatively, it might plateau, leaving the universe a cold, empty wasteland where no new stars form. Or perhaps dark energy will fade, allowing gravity to finally pull everything back together in a big crunch. Each scenario hinges on dark energy's true nature, a puzzle we're no closer to solving. What's clear is that dark energy forces us to confront profound questions about reality's fabric. Is the accelerating expansion a clue to unseen dimensions or new physics beyond Einstein? Does it hint at multiple universes with different dark energy strengths, most inhospitable to life? One thing's certain: the universe's ultimate fate isn't written in the stars, but in the invisible, enigmatic force that fills the void between them. What if our universe is just one page in an infinite cosmic library, where every possible variation of physical laws exists somewhere in the vast multiverse? This isn't science fiction, it's the multiverse hypothesis, one of the most debated ideas in modern cosmology. The concept springs from a startling implication of eternal inflation, the theory that our Big Bang was just one bubble among countless others in an ever-expanding quantum foam. Picture a boiling pot of water where each rising bubble is an entire universe, some with physics like ours, others with unrecognizable rules, stronger gravity, no electromagnetism, or even extra dimensions folded in on themselves. String theory, the ambitious framework aiming to unify all forces of nature, adds fuel to this fire. It suggests there could be 10 to the 500 possible configurations of spacetime, a landscape of universes where constants like the strength of gravity or the mass of an electron are shuffled like a cosmic deck of cards. In some, matter might never clump into galaxies. In others, atoms could be unstable, rendering life impossible. This dizzying diversity raises a profound question. Are we here because our universe's laws are special, or is it sheer luck in a cosmic lottery with near-infinite tickets? Proponents like Max Tegmark argue this isn't just speculation, but a natural extension of physics. His mathematical universe hypothesis goes even further, suggesting every mathematically possible structure exists as a physical reality. Critics like Paul Steinhardt, however, see a dangerous shift from testable science to untestable philosophy. Without observable evidence, they argue, the multiverse risks becoming a theory of anything, able to explain everything but predict nothing. Yet there might be ways to probe this unseeable realm. Some theorists suggest collisions between bubble universes could leave imprints in the cosmic microwave background, like bruises on spacetime. Others hunt for anomalies in the distribution of galaxies or the behavior of dark energy that might hint at a larger cosmic fabric. Even if definitive proof eludes us, the multiverse pushes a deeper question. What does it mean to do science when the subject lies forever beyond our horizon? Whether a groundbreaking truth or a tantalizing dead end, this idea forces us to confront the very limits of knowledge and wonder what other realities might be lurking just out of sight. The Big Bang theory may dominate modern cosmology, but it's far from the only idea attempting to explain the universe's origins. Take the cyclic model, a vision of time without beginning or end, where our universe is just one chapter in an infinite series of expansions and contractions. In this framework, the Big Bang wasn't a singular starting point but a transition, a moment when a previous universe collapsed and rebounded like a cosmic inhale and exhale. The appeal, it sidesteps the singularity problem entirely, replacing that enigmatic starting point with a smoother, cyclical process. Yet for all its elegance, the cyclic model struggles to explain the universe's observed uniformity or the precise ratios of light elements we see, details the Big Bang nails with startling accuracy. Then there's bouncing cosmology, a close cousin that imagines the universe contracting to a near singularity before quantum effects trigger a rebound. Unlike the classical Big Bang, this bounce avoids infinite density by invoking repulsive forces from quantum gravity. Supporters point to subtle anomalies in the cosmic microwave background, potential echoes of a pre-bounce universe, but these remain speculative. Without definitive proof, bouncing cosmologies linger in the realm of fascinating what-ifs. Perhaps the most radical challenger is the holographic principle, which suggests our three-dimensional universe might be a projection of information encoded on a two-dimensional surface at its boundary. Imagine the cosmos as a cosmic movie screen, with every event inside merely shadows cast by data flickering at the edges. This mind-bending idea emerges from black hole physics, where calculations show the information inside a black hole scales with its surface area, not volume. If true, it would revolutionize our understanding of space, time, and even the Big Bang itself. but like other alternatives, tangible evidence remains elusive. What's remarkable is how these theories highlight science's self-correcting nature. The Big Bang reigns not because it's perfect, it has gaps, like the Singularity and what preceded inflation, but because it fits more observations than any rival. Yet history shows even the best theories evolve. Future telescopes probing primordial gravitational waves or quantum gravity experiments could tilt the scales overnight. Until then, the cosmos keeps its deepest secrets close, reminding us that every answer uncovers new questions waiting in the dark. For all we've uncovered about the cosmos, the deepest mysteries still taunt us with their elusiveness. Take the Big Bang itself, we can trace the universe's expansion back to that fiery birth. But what ignited it? Was there truly nothing before? Or does our concept of nothing simply fail to capture a more exotic precursor? Some theorists propose quantum fluctuations in a primordial vacuum, while others imagine colliding membranes in higher dimensions. The unsettling truth is that our physics reaches its limits at the Singularity, leaving us staring into an abyss of unknowns. Then there's the universe's eerie fine-tuning, the fact that dozens of physical constants are balanced with knife-edge precision to allow galaxies, stars, and life itself. Alter the strength of gravity by just 1 part in 10 to the 60th power, and stars would never form. Tweak the cosmological constant slightly, and the universe would either collapse instantly or expand too rapidly for structure to emerge. This cosmic Goldilocks problem has led to radical explanations. Is our universe one fortunate outcome in a vast multiverse, or do these just right conditions hint at deeper laws we've yet to grasp? Dark matter and dark energy compound the puzzle. We've mapped dark matter's gravitational fingerprints across galaxy clusters and the cosmic web, but after decades of hunting, no particle has shown itself in detectors. Could it be an undiscovered heavyweight in the particle zoo, or something more exotic like primordial black holes forged in the Big Bang's first second? Dark energy is even more perplexing. Its apparent uniformity suggests it's an intrinsic property of space itself, yet its measured strength contradicts quantum theory's predictions by a staggering 120 orders of magnitude. This isn't just a gap in knowledge, it's a canyon. The quest for answers is driving a new generation of cosmic explorers. The James Webb Space Telescope peers deeper into the infrared than ever, capturing light from the universe's first galaxies to probe how dark matter shaped their growth. Meanwhile, CERN-planned future circular collider would smash particles at energies nearing those of the Big Bang, potentially creating dark matter in the lab or revealing extra dimensions. On Earth, experiments like Elusive Zeppelin hunt for dark matter's faint whispers in vats of liquid xenon buried miles underground, while next-gen telescopes like the Vera Rubin Observatory scan the skies for subtle distortions caused by dark energy's push. What's astonishing isn't just how much we don't know, it's how brilliantly we've learned to ask the questions. From Galileo's first telescope to Webb's gold-plated mirrors, each tool extends our vision further into the dark. The universe may guard its secrets fiercely, but with every unanswered riddle, it offers new clues. And somewhere in those clues lies not just the story of where we came from, but perhaps where we're headed in this vast, unfolding cosmic drama. Symmetry wasn't just a feature of the early universe, it was the foundation of reality itself. Picture a cosmic ballet where every particle and force moved in perfect unison, indistinguishable from one another. In those first moments after the Big Bang, the 4 fundamental forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, were fused into a single, symmetrical superforce. It was a state of pure harmony where the rules of physics were so unified that even matter and energy danced to the same rhythm. But this symmetry couldn't last. As the universe cooled, cracks began to form in this flawless cosmic mirror, and with each break, the diversity of our universe emerged. The first dramatic split occurred when the electroweak force, a merger of electromagnetism and the weak nuclear force, fractured into two distinct forces. This wasn't just a subtle shift, it was a cosmic phase transition, like water freezing into ice. The Higgs field, an invisible energy saturating all of space, played the starring role. As temperatures dropped below 1 trillion degrees, this field switched on like a cosmic spotlight, interacting with particles in a way that gave them mass. Some particles, like quarks and electrons, trudged through this newfound molasses, slowing down and gaining heft. Others, like photons, remained weightless, zipping through the universe untouched. This asymmetry didn't just create mass, it set the stage for atoms, chemistry, and ultimately, life. The hunt for deeper symmetries drives one of physics' most ambitious quests, the grand unified theory. Scientists suspect that before the electroweak split, the strong nuclear force which glues atomic nuclei together might have also been part of this unified force. Evidence lies in the way particles behave at extreme energies. In particle colliders, when we smash matter together at near light speeds, we catch glimpses of these long-lost symmetries re-emerging, as if the universe briefly remembers its original state. Yet full unification remains elusive. The math suggests these forces should converge at energies so high they'd require a particle accelerator the size of a galaxy to test directly. What's tantalizing is the possibility that even deeper symmetries lurk in the universe's first slivers of time. Perhaps a single, elegant principle governing all forces, including gravity. String theory and other frameworks propose hidden dimensions or supersymmetry, where every known particle has a heavier, unseen twin. If these ideas hold, they'd rewrite our understanding of the Big Bang's earliest moments, revealing a cosmos far simpler and more symmetrical than the fractured reality we see today. The universe's greatest trick might be hiding its true unity beneath layers of broken symmetry, waiting for us to piece it back together. In the seething quantum foam of the early universe, reality behaved in ways that defy common sense. At scales trillions of times smaller than an atom, particles flickered in and out of existence, virtual pairs born from nothingness, surviving just long enough to leave their mark before vanishing again. These quantum fluctuations might seem insignificant, but inflation acted like a cosmic magnifying glass, stretching those subatomic tremors across the entire sky. Picture a single ripple on a pond suddenly expanding until it becomes a tidal wave wider than a continent. That's what happened to those quantum wrinkles. What began as fleeting imbalances smaller than a proton were inflated to scales spanning millions of light years. The magic lies in how these microscopic imperfections became cosmic blueprints. As inflation stretched space-time, it froze those quantum jitters into the fabric of the universe, creating regions where matter was ever so slightly denser or sparser. These variations, just one part in 100,000, might seem trivial, but gravity thrives on imbalance. Over billions of years, those slightly denser patches pulled in more matter, growing like snowballs rolling downhill until they became galaxies and galaxy clusters. Meanwhile, the emptier regions stretched into vast cosmic voids. The result, a universe sculpted by quantum randomness into the intricate cosmic web we observe today. Modern galaxy surveys like the Sloan Digital Sky Survey reveal this legacy in stunning detail. When astronomers map millions of galaxies, they don't see random scatter. They find patterns matching the statistical fingerprints of quantum noise amplified by inflation. It's like discovering that every mountain range on Earth traces back to microscopic cracks in a single grain of sand. Even more astonishing is how precisely these patterns align with predictions. The distribution of galaxies, the spacing between clusters, even the way light bends around massive objects, all echo those primordial quantum whispers. But the quantum story doesn't end there. The same principles that seeded galaxies might also govern the most enigmatic objects in the cosmos, black holes. At their event horizons, particles constantly emerge from quantum fluctuations, some escaping as Hawking radiation while others fall inward. This dance between creation and annihilation hints at a deeper truth, that quantum mechanics and gravity are entwined in ways we're only beginning to fathom. Perhaps black holes, like the early universe, are writing their history in the language of quantum uncertainty, a reminder that the smallest and largest scales of reality are far more connected than we ever imagined. Black holes aren't just cosmic vacuum cleaners, they're information shredders, or so we once thought. When Stephen Hawking first calculated that black holes should slowly evaporate by emitting radiation, he stumbled upon a paradox that's haunted physicists for decades. If a black hole eventually vanishes, what happens to all the information about the stars, planets, and gas it swallowed? Quantum mechanics insists information can't be destroyed. It might get scrambled, but it's always preserved, like shuffling a deck of cards. Yet general relativity suggests black holes erase information permanently, crushing it into a singularity where even the laws of physics break down. This clash isn't just academic, it hints at a fundamental flaw in our understanding of reality. The stakes get even higher when we connect this to the Big Bang. If black holes can erase information, could the universe's birth have done the same? The initial singularity might have been the ultimate information wipe, a cosmic reset button, but holography, a radical idea born from string theory, offers a way out. It proposes that all the information within a volume of space, like a black hole's interior, is actually encoded on its surface like a cosmic QR code. The AD/S/CFT correspondence takes this further, suggesting a black hole's event horizon acts as a holographic screen, preserving information in a way we're only beginning to decipher. Suddenly, the paradox softens. Information isn't lost, just translated into a language we don't yet understand. Recent breakthroughs add fuel to the fire. Experiments with quantum entanglement show particles can share information instantaneously across vast distances, defying classical notions of spacetime. Some theorists argue this hints at spacetime itself being emergent, a secondary effect of deeper, more fundamental processes, like how temperature emerges from the motion of atoms. If true, it would mean the smooth, continuous universe we perceive is just the surface of something far stranger, a cosmic illusion woven from quantum threads. So where does this leave the Big Bang? If spacetime is emergent, its singularity might not be a true beginning but a phase transition, like ice melting into water. The information we think was created at the Big Bang could have been transformed, not conjured from nothing. It's a dizzying thought. The universe's origin might not be a single, isolated event, but a ripple in something deeper, a cosmic code we're still learning to read. As we peel back these layers, we're left wondering, is the ultimate answer to the universe's birth written not in the stars, but in the very fabric of information itself? The universe has a built-in direction, an arrow that points relentlessly from past to future, but why? The answer lies in entropy, the measure of disorder that gives time its one-way street. Picture a deck of cards fresh from the box, perfectly ordered by suit and number. That's the low entropy state of the early universe, a pristine, improbable arrangement where matter and energy were concentrated in an almost unimaginably dense, uniform soup. The moment the Big Bang unleashed expansion, entropy began its inevitable climb, like shuffling that deck into ever greater chaos. Stars forming, galaxies colliding, even the heat from your morning coffee dissipating. all are part of this cosmic trend toward disorder. But here's the puzzle. If entropy always increases, why did the universe start with such unnaturally low entropy to begin with? Physicist Ludwig Boltzmann proposed a radical alternative, that time's arrow might just be a statistical fluke. In an infinite universe, he argued, even the most improbable states will occasionally arise purely by chance. Imagine a room full of air molecules spontaneously clustering in one corner, vanishingly unlikely, but not impossible given enough time. Boltzmann suggested we might be living in such a random fluctuation, a temporary bubble of order in an otherwise chaotic cosmos. Yet this raises a haunting question. If time's arrow is just luck, why don't we remember events in both directions? Why do smashed glasses never reassemble on tables? Enter Maxwell's demon, a thought experiment that exposes entropy's deepest mysteries. Imagine a tiny, intelligent being controlling a trapdoor between two gas-filled chambers. By letting only fast-moving molecules pass one way and slow ones the other, the demon could, in theory, reduce entropy without expending energy, violating thermodynamics. The resolution, information itself, has an entropy cost. Every time the demon measures a molecule's speed, it generates heat, preserving the universe's relentless march toward disorder. This revelation ties entropy not just to energy, but to the very fabric of information and computation. Could time's arrow ever point differently, in a multiverse with alternate physics, perhaps? Some theories suggest universes with reversed entropy might exist, where broken cups leap back into hands and memories form of the future. Others propose cyclical cosmologies where entropy resets with each new Big Bang. For now, these remain speculative, but they remind us that our experience of time may be just one thread in a vast, woven tapestry of possibilities. What if the arrow isn't universal, but local, bending in ways we've yet to imagine? The answer might lie not in the familiar rhythms of our cosmos, but in the untested laws of realities beyond. Imagine a universe where matter and antimatter existed in perfect balance, a cosmos where every particle had its mirror twin. Such a universe would have annihilated itself in a flash of pure energy, leaving behind nothing but empty space. Yet here we are, surrounded by galaxies, stars, and planets made of matter. This cosmic lopsidedness, the fact that we exist at all, is one of the universe's most profound puzzles. Scientists call it baryogenesis, the process that tipped the scales in favor of matter, leaving just enough survivors to build everything we see. The mystery starts with the Big Bang's fiery aftermath. In those first moments, particle collisions should have produced equal amounts of matter and antimatter, which would then have annihilated each other completely. But something broke this symmetry, leaving behind roughly one extra matter particle for every billion annihilations. The question is, what? Russian physicist Andrei Sakharov outlined three essential conditions for this imbalance: a universe out of thermal equilibrium, processes that treat matter and antimatter differently, CP violation, and interactions that can change the total number of particles. While we've observed CP violation in quarks, it's far too weak to explain the universe's matter dominance. Enter leptogenesis, a compelling twist on the story. This theory suggests the imbalance might have started with neutrinos, those ghostly particles that barely interact with matter. In the early universe, heavy hypothetical particles called right-handed neutrinos could have decayed asymmetrically, producing slightly more matter than antimatter. Over time, these decays would have transformed into the baryon asymmetry we see today. Experiments like T2K in Japan are hunting for signs of this by firing neutrino beams through detectors, watching for telltale differences in how neutrinos and antineutrinos oscillate between flavors. Even a tiny bias in these oscillations could reveal the mechanism behind our matter-filled existence. Another contender is electroweak baryogenesis, where the Higgs field plays a starring role. As the universe cooled after inflation, the Higgs field underwent a phase transition, like water freezing into ice creating bubbles of lower energy space that expanded and collided. These collisions could have generated the out-of-equilibrium conditions Sakharov described, while interactions with the Higgs field preferentially produced matter over antimatter. The challenge: current measurements suggest this transition wasn't dramatic enough to create the observed asymmetry, unless undiscovered particles were involved. That's where sterile neutrinos come in, theoretical particles even more elusive than their ordinary cousins. If they exist, they could have interacted with the Higgs field in ways that amplified matter production. Experiments like the upcoming Deep Underground Neutrino Experiment, DUNE, aim to test these ideas by probing neutrino behavior with unprecedented precision. The stakes couldn't be higher. If sterile neutrinos are confirmed, they might not just solve the matter-antimatter puzzle, they could also be the key to dark matter. What's breathtaking is how finely tuned this imbalance had to be for life to exist. A slightly weaker asymmetry, and the universe would have been too empty for galaxies to form. A stronger one, and dense matter would have collapsed into black holes long before planets could emerge. In this delicate dance between creation and annihilation, we find yet another example of cosmic fine-tuning, a universe that somehow got the recipe just right. The search for answers isn't just about understanding the past, it's about uncovering whether our matter-rich reality was inevitable or a stroke of unimaginable luck. The numbers governing our universe are so precise that altering any one of them by even a hair's breadth would render life impossible. Take the cosmological constant, the value dictating how fast the universe expands. If it were slightly stronger, galaxies would have been ripped apart before stars could form. A fraction weaker, and gravity would have collapsed everything back into a singularity almost immediately. The Higgs mass is another cosmic tightrope walk. If it were just a few % different, atoms wouldn't bond, chemistry wouldn't exist, and the universe would be a lifeless void. These aren't isolated quirks. Over 30 physical constants exhibit this razor-thin fine-tuning, each balanced with the precision of a master watchmaker. This eerie perfection has led some to propose the anthropic principle, the idea that the universe appears designed for life simply because we're here to observe it. In other words, if conditions weren't just right, we wouldn't exist to ponder them. It's like a puddle marveling at how perfectly its hole fits its shape. But this explanation feels unsatisfying. It doesn't explain why the hole exists in the first place. Enter the multiverse. If countless universes bubble into existence with random physical constants, most would be sterile, but a rare few would, by sheer chance, hit the jackpot. We'd inevitably find ourselves in one of the lucky ones. String theory's landscape of possible universes lends mathematical weight to this idea, suggesting a cosmic lottery where every conceivable set of laws plays out somewhere. Yet critics argue this simply kicks the can down the road. What determines the rules governing the multiverse itself? Others hunt for deeper laws that might explain fine-tuning naturally. Could a yet undiscovered symmetry or principle lock constants into their life-friendly values? Some theories suggest these numbers aren't arbitrary, but emerge from the geometry of hidden dimensions or the self-consistency of mathematical structures. The Higgs mass, for instance, might be tied to the behavior of supersymmetric particles we haven't detected yet. The stakes couldn't be higher. If fine-tuning points to a multiverse, it rewrites our understanding of reality. If it hints at undiscovered physics, it's a roadmap to unification. And if it's mere coincidence, well, the odds are so astronomically slim that even calling it luck feels inadequate. Perhaps the answer lies in a radical rethink of what a law of nature even is, not fixed decrees, but dynamic relationships emerging from something far more fundamental. Whatever the truth, fine-tuning isn't just a puzzle. It's a beacon guiding us toward the next revolution in physics. Deep in the shadows of the cosmic microwave background lurks an even older relic, neutrinos, the universe's most elusive messengers. Born just 1 second after the Big Bang, these ghostly particles have been streaming through space for nearly 14 billion years, passing through planets, stars, and even you at nearly the speed of light. Billions of cosmic neutrinos flow through your thumbnail every second, leaving no trace. Unlike photons in the CMB, which were set free 380,000 years after the Big Bang, these neutrinos carry whispers from the universe's very first moments, a time so hot and dense that even atomic nuclei couldn't hold together. Detecting this cosmic neutrino background is like trying to catch smoke with your bare hands. Neutrinos barely interact with matter. They're so indifferent to the rest of the universe that most pass through Earth as if it weren't even there. But projects like Ptolemy are rising to the challenge. Using ultra-pure materials chilled to near absolute zero, these experiments aim to spot the faintest vibrations caused by relic neutrinos, akin to hearing the echo of a whisper in a hurricane. If successful, they'd open a window into an era before the CMB, revealing how the universe behaved when it was just a seething soup of fundamental particles. What makes these neutrinos so valuable is their stubbornness. While the CMB photons were scattered and reshuffled during recombination, cosmic neutrinos have traveled unimpeded since their creation, preserving a pristine snapshot of the early universe's conditions. Their patterns could unveil secrets about inflation, the formation of the first nuclei, even the mysterious imbalance between matter and antimatter. Some theories suggest relic neutrinos might have subtly influenced how galaxies clustered, leaving faint gravitational fingerprints in the large-scale structure of the cosmos. But their ghostly nature also makes them cosmic spies. When a star explodes as a supernova, 99% of its energy blasts out in neutrinos, often arriving hours before the light as they escape the collapsing core unimpeded. Detectors like Supercomputers and in Japan have captured these stellar death cries, offering real-time alerts to astronomers. Even more tantalizing is the possibility that neutrinos could be tied to dark matter. Certain theoretical particles, like sterile neutrinos, might interact only through gravity while leaving traces in the neutrino background we're only beginning to decode. The hunt for these primordial phantoms isn't just about looking backward, it's about testing the limits of physics itself. If we can pin down relic neutrinos, we might finally understand why the universe tipped toward matter, how inflation truly unfolded, or even whether hidden dimensions exist. They're whispers from the dawn of time, and we're only just learning how to listen. Gravitational waves aren't just ripples in space, they're echoes from the universe's birth, carrying secrets older than light itself. In 2015, the LIGO Observatory made history by detecting these space-time wrinkles from colliding black holes over 1 billion light-years away. But that groundbreaking moment was just the beginning. Hidden in the faint tremors of the cosmos might be an even more profound signal: primordial gravitational waves, generated during inflation's explosive growth in the first trillionth of a second after the Big Bang. Unlike the cosmic microwave background, which shows us the universe 380,000 years post-Bang, these waves could be our only direct window into the Planck epoch, a time when gravity itself behaved as a quantum force. Picture spacetime as a vast ocean. The collisions LIGO observes are like tsunamis from distant storms, while primordial waves would be the subtle swells left by the ocean's very creation. Detecting them would confirm that inflation wasn't just theoretical. It was a violent, quantum-driven process that stretched spacetime faster than light. The telltale signature, a unique curling pattern in the polarization of the CMB called B modes, which would have been imprinted as inflation's gravitational waves interacted with photons. Experiments like BICEP and the South Pole Telescope have hunted for this fingerprint, though cosmic dust has so far muddied the signal. The real game changer lies ahead. Space-based detectors like LISA, set to launch in the 2030s, will bypass Earth's seismic noise to listen for gravitational waves at frequencies too low for ground-based instruments. Freed from these constraints, LISA could catch whispers from the universe's first microseconds, or even uncover evidence of cosmic strings, hypothetical defects in spacetime left over from the Big Bang. Think of it as giving cosmology a new sense, like switching from grainy black and white photos to high-definition video. What's at stake isn't just technical, it's philosophical. If we can probe the Planck epoch, we might glimpse physics beyond Einstein, where gravity and quantum mechanics unite. Some theories predict primordial waves so faint they'll never be detected. Others suggest they're just beyond our current reach. Either way, the hunt reshapes our understanding of reality's fabric, turning spacetime's subtle shivers into a language we're only beginning to decipher. The universe's ultimate fate hinges on a cosmic tug of war between expansion and entropy, a battle that could end in icy silence or dramatic rebirth. Heat death, the most widely accepted scenario, paints a chilling portrait of the far future. As dark energy accelerates galaxies apart, star formation will sputter out, leaving the cosmos a graveyard of black holes and dead stars. Over trillions of years, even these remnants will evaporate via Hawking radiation, until only a dilute sea of photons and subatomic particles remains. Entropy reaches its maximum. No more work can be done, no structures form. The universe becomes a featureless void, its temperature uniform to the last decimal point. It's a lonely finale where time itself loses meaning. No change means no way to measure its passage. Yet not all physicists accept this frozen fate. Sir Roger Penrose's conformal cyclic cosmology proposes a dazzling alternative. The universe doesn't end but reincarnates. When all matter decays into radiation, spacetime loses its sense of scale. An infinite expanse becomes indistinguishable from an infinitesimal point. In this state, Penrose argues, the universe resets, triggering a new Big Bang. Strikingly, he claims evidence for this in the cosmic microwave background, concentric rings of temperature variations he interprets as gravitational wave echoes from previous cosmic cycles. While controversial, the idea offers poetic symmetry, death and rebirth woven into the fabric of reality. String theory's landscape of possible universes adds another twist. If eternal inflation spawned our bubble universe, others may exist with different physics, some collapsing, others expanding endlessly. This multiverse wouldn't have a single fate but a spectrum of endings. Some bubbles might even host civilizations that engineer their own survival, harnessing black hole energy or transcending physical form. The late Freeman Dyson speculated that advanced intelligence could slow entropy's march by operating in slower, cooler epochs, stretching thought across eons. Could consciousness outlast the cosmos? The challenges are staggering. In a heat-death scenario, energy gradients vanish, the lifeblood of computation. Yet some theorize that quantum fluctuations might still allow sporadic computation, enabling minds to persist at glacial speeds. Others imagine civilizations migrating to younger universes through black hole singularities or constructed wormholes. Far-fetched perhaps, but the mere possibility reframes the cosmic story, not as a futile march toward chaos, but as a challenge to life's ingenuity. After all, if the universe could arise from quantum foam, who's to say intelligence couldn't sculpt its own destiny within it? The final chapter isn't written yet. It might just be waiting for us to turn the page. Supercomputers have become our most powerful time machines, capable of rewinding the universe's history back to its fiery beginnings. Take ENSO, one of the most sophisticated cosmic simulation codes. It doesn't just model galaxies or stars. It recreates the entire evolution of the cosmos from first principles, starting with the raw ingredients of the Big Bang, dark matter, hydrogen, and the faint quantum seeds of structure. The results are breathtaking. When astronomers compare these virtual universes to real sky surveys, the distributions of galaxies match with uncanny precision, as if the simulations had peeked into nature's blueprint. It's like watching a trillion-piece jigsaw assemble itself exactly as predicted, down to the sprawling filaments of the cosmic web. Yet these digital cosmos also reveal glaring gaps in our understanding. While they nail the large-scale structure, small-scale mysteries persist, like the too big to fail problem, where simulated dark matter halos appear denser than the faint dwarf galaxies we observe. This discrepancy hints that dark matter might be more complex than we thought, or that feedback from early stars scrambled small-scale structure in ways we're still decoding. Some simulations even suggest dark matter could interact with itself, creating friction that smooths out clumps. Others propose wilder ideas, like primordial black holes formed in the Big Bang's first second. Each tweak to the code is a test of our theories, turning supercomputers into laboratories for the impossible. What's astonishing is how much of this cosmic detective work now involves the public. Projects like Universe at Home let anyone donate idle computer time to run simulations, searching for rare galaxy mergers or testing alternative physics. It's a democratization of cosmology, where a high school student's laptop might help crack a problem that stumped professionals for decades, and the next leap. Quantum computers, classical machines, hit walls when simulating the quantum froth of the universe's first moments, but quantum bits could finally model inflation's chaotic energy fields or the singularity itself. Imagine probing Planck-scale physics not with equations, but by recreating it in a quantum matrix, a virtual Big Bang running on hardware that mirrors the quantum rules of the early cosmos. These simulations aren't just exercises in coding, they're bridges between theory and observation, revealing where our models shine and where they shatter. Every mismatch between simulation and reality isn't a failure, it's a clue, a whisper from the universe that there's something fundamental we've yet to grasp. And with each iteration, we inch closer to answering the ultimate question. Did our universe have to unfold this way, or was it just one roll of the cosmic dice? Humanity has always stood beneath the stars asking two fundamental questions. How did everything begin, and does that beginning carry meaning? Science gives us the Big Bang, an event backed by equations and evidence, where quantum fluctuations in a primordial vacuum sparked the birth of space-time. Yet this clinical explanation brushes against something deeper in us, an ancient longing to know not just the mechanics of creation, but whether it was meant to be. Every culture has grappled with this duality. The Norse told of a cosmic giant, Ymir, whose body became the world. The Aboriginal Dreamtime speaks of ancestral spirits singing the land into existence. These aren't just stories, they're attempts to weave purpose into the fabric of reality, to find a why nestled within the how. Science, by its nature, avoids the language of intention. When we ask why the Big Bang happened, physics offers probabilities, quantum tunneling from nothingness, or perhaps a collision of higher dimensional brains. But the human mind rebels at pure chance. We search for patterns, for narratives that cast us as more than accidents in an indifferent void. This tension isn't a flaw, it's a testament to our dual nature. We are stardust that has learned to measure its own composition, creatures who can chart cosmic expansion while still aching to know if love and beauty are echoes of something universal. Perhaps the bridge between these realms lies in the tools we've built to observe creation. Telescopes like JWST don't just collect photons, they translate the universe's autobiography into a language we can understand. Each image of a newborn galaxy is both data and metaphor, a reminder that the same laws forging stars also forge the eyes that study them. The Higgs field, the cosmic web, even dark energy's relentless push, these aren't just phenomena. They're characters in a story where the observer has become part of the narrative. Science may never answer why there's something rather than nothing, but in revealing how finely tuned that something is, it offers its own kind of poetry, a cosmos that seems, against all odds, to have wanted to be known. The Hubble Space Telescope didn't just capture images of the cosmos, it opened a window to the past. In 1995, astronomers pointed Hubble at a seemingly empty patch of sky, no larger than a grain of sand held at arm's length. What they found was staggering, a treasure trove of over 3,000 galaxies, some so distant their light had traveled for over 13 billion years to reach us. This iconic Hubble Deep Field image transformed our understanding of the universe's youth, revealing galaxies in their chaotic infancy, brimming with star formation and collisions. It was like unearthing a cosmic photo album, each snapshot capturing a different chapter of the universe's story. But Hubble was just the beginning. The James Webb Space Telescope, with its gold-plated mirrors and infrared eyes, peers even further back in time, to an era when the universe was a mere 200 million years old. Unlike Hubble, which sees mostly visible light, JWST detects the infrared glow of those first stars and galaxies, their light stretched into longer wavelengths by the expansion of space itself. Early targets include GNZ11, a galaxy so distant we see it as it was just 400 million years after the Big Bang. The real prize, population 3 stars, hypothetical giants made purely of hydrogen and helium, forged in the universe's fiery dawn. These celestial behemoths, hundreds of times more massive than our Sun, would have lived fast and died young, seeding the cosmos with the first heavy elements. Spotting them would be like finding the fossilized bones of the universe's very first architects. The next generation of observatories promises even greater revelations. The extremely large telescope, with a mirror nearly half the size of a football field, will dissect the atmospheres of exoplanets orbiting distant stars, hunting for biosignatures like oxygen or methane. Meanwhile, the Nancy Grace Roman Space Telescope will map the cosmos in unprecedented detail, capturing the equivalent of 100 Hubble Deep Fields in a single sweep. Its wide-field surveys could uncover millions of galaxies, tracing the invisible web of dark matter that binds them together. What's thrilling is how these instruments don't just observe the universe, they redefine its timeline. JWST early data has already hinted that some galaxies matured faster than our models predicted, suggesting gaps in our understanding of cosmic evolution. Future telescopes might uncover even more surprises, perhaps evidence of stars born before galaxies, or relics from a pre-Big Bang universe. Each new observation is a thread in a tapestry we're still weaving, connecting the first sparks of light to the sprawling cosmos we call home. The deeper we look, the more we realize the universe's story is far richer and stranger than we ever imagined. Deep beneath the French-Swiss border lies the world's most powerful time machine, the Large Hadron Collider. This 27-kilometer ring of superconducting magnets doesn't just accelerate particles to near light speeds, it recreates conditions unseen since the universe's first microseconds. When lead nuclei collide inside its detectors, temperatures soar to over 5 trillion degrees, 100,000 times hotter than the Sun's core. For a fleeting instant, the LHC tears apart the fabric of matter itself, melting protons and neutrons into a primordial soup called quark-gluon plasma. This isn't just plasma, it's the universe as it existed before atoms, before stars, even before stable particles had formed. The discoveries here have rewritten textbooks. Quark-gluon plasma behaves less like a gas and more like a perfect liquid, with virtually zero viscosity. Particles within it move in lockstep, as if choreographed by some unseen quantum hand. This finding shocked physicists who expected something more chaotic. It suggests that the infant universe was far more interconnected than we imagined, with particles communicating across distances that should have been impossible. Even more intriguing are hints of strangelets, hypothetical chunks of strange quark matter that might have formed in those first chaotic microseconds. If confirmed, they could explain dark matter or even reveal new states of matter lurking in neutron stars. But the LHC's crown jewel remains the Higgs boson, discovered in 2012. This particle is the physical manifestation of the Higgs field, the cosmic molasses that gives all matter its mass. Finding it completed the standard model, but it also raised new questions. The Higgs is oddly light, so light that quantum corrections should have made it impossibly heavy unless unknown particles are balancing the scales. This discrepancy points to physics beyond the standard model, perhaps supersymmetry or hidden dimensions. The next leap, the Future Circular Collider, a proposed 90-kilometer behemoth that could reach energies 7 times higher than the LHC. Imagine probing the electroweak epoch directly, or creating particles so heavy they've never existed naturally since the Big Bang's first trillionth of a second. Some theories suggest such energies might even generate microscopic black holes, not the destructive kind, but fleeting quantum ones that could reveal how gravity behaves at the smallest scales. What's revolutionary is how these experiments bridge cosmology and particle physics. When colliders recreate quark-gluon plasma, they're testing models of the early universe's expansion. When they hunt for dark matter candidates, they're probing the invisible scaffolding of galaxies. Even failed searches matter, every null result narrows the possibilities, steering theorists toward new ideas. It's a dance between the unimaginably vast and the infinitesimally small, where the secrets of the cosmos are hiding in subatomic debris. The universe seems almost suspiciously hospitable to life, not just in its sprawling vastness, but in the razor-thin precision of its physical constants. Tweak the strength of gravity by a fraction and stars would never ignite. Adjust the cosmological constant slightly, and galaxies would tear apart before forming. This eerie fine-tuning has led scientists to propose the anthropic principle, the idea that the universe's laws appear perfectly calibrated for life because, well, we're here to observe them. It's a cosmic version of the old saying, if the universe weren't fit for life, we wouldn't be around to question it. But this principle comes in 2 flavors, each with radically different implications. The weak anthropic principle is the less controversial cousin. It simply states that we must find ourselves in a region of the universe compatible with our existence. Imagine a fish marveling that water is perfectly suited for swimming. It's not that water was designed for fish, but that fish evolved to thrive in water. Similarly, our universe's constants might be one possibility among many, and we're just the lucky observers in the slice of reality where life can emerge. This version doesn't demand deeper meaning. It's a statistical observation, a cosmic selection effect. The strong anthropic principle, however, ventures into bolder territory. It suggests a more profound link between consciousness and the universe's very structure. that life isn't just an accidental passenger but somehow entwined with the laws of physics themselves. Some interpretations even flirt with the idea that the universe requires observers to bring it into full reality, echoing quantum mechanics' observer effect on a cosmic scale. This isn't just philosophy. Nobel laureate Eugene Wigner once speculated that consciousness might play a role in collapsing quantum wave functions. While tantalizing, critics argue the strong version strays into untestable metaphysics. Is it science or a cleverly disguised tautology, a circular argument that says the universe is life-friendly because we're alive to see it? Exoplanet discoveries are quietly reshaping this debate. As we catalog thousands of worlds, we're finding that Earth-like planets orbiting in habitable zones might be astonishingly common. If life emerges readily under the right conditions, the weak anthropic principle gains ground. Our existence could just be a happy accident in a vast, life-permitting cosmos. But if, despite countless opportunities, life remains vanishingly rare, the strong version's hints of deeper fine-tuning grow louder. Missions like JWST are now sniffing the atmospheres of distant worlds for biosignatures, turning what was once philosophical speculation into an empirical question. Underlying all this is a humbling truth. We still don't know whether life is a cosmic fluke or an inevitable outcome of physics. The anthropic principle, in all its forms, forces us to confront the limits of our perspective. Are we the universe's intended audience, or just fleeting stardust that briefly learned to ask why? The answer might lie not in grand theories, but in the silent chemistry of alien oceans or the faint radio whispers of civilizations long gone. Until then, we're left with a cosmos that feels, against all odds, like it was waiting for us to arrive. For centuries, Earth stood alone in our imagination, a singular oasis of life in a seemingly barren cosmos. But the discovery of exoplanets shattered that illusion, revealing a universe teeming with worlds beyond our solar system. The Kepler Space Telescope alone confirmed over 2,600 planets orbiting distant stars, with estimates suggesting billions more in our galaxy. Some orbit so close to their stars that their surfaces are molten rock. Others drift in eternal frozen darkness. But nestled between these extremes are the Goldilocks worlds, planets where temperatures might allow liquid water to pool on their surfaces, that delicate ingredient we believe essential for life as we know it. This cosmic census forces us to confront two competing visions of our place in the universe. The rare Earth hypothesis argues that Earth's precise conditions, its stable orbit, protective moon, magnetic field, and plate tectonics, make it extraordinarily unique. Even in a galaxy brimming with planets, the alignment of factors needed for complex life might be vanishingly rare. Yet the mediocrity principle pushes back, suggesting there's nothing particularly special about Earth or our Sun. With hundreds of billions of stars in the Milky Way, even unlikely conditions are bound to repeat countless times. The truth likely lies somewhere in between. While rocky planets in habitable zones may be common, the path from chemistry to biology, let alone intelligence, could be strewn with obstacles we're only beginning to understand. Consider the TRAPPIST-1 system, 39 light-years away, where 7 Earth-sized worlds orbit a dim red dwarf star. 3 sit squarely in the habitable zone, but their proximity to their star means they're likely tidally locked, one side perpetually scorched, the other frozen. Could life cling to existence in the slender twilight between, or take K2-18b, a super-Earth with water vapor in its atmosphere? Its enormous gravity might crush any chance of complex life, but microbial organisms could thrive in its deep oceans. These discoveries don't just expand the catalog of worlds, they force us to rethink what habitability even means. Life on Earth thrives in boiling vents, acidic pools, and Antarctic ice. Who's to say it couldn't adapt to environments we'd consider hellish? This explosion of exoplanet data also reignites the fine-tuning debate. If life requires such precise conditions, does that imply the universe's constants were deliberately set to allow it? Or does the sheer abundance of worlds make life's emergence inevitable through sheer probability? The answer might lie in the coming decades, as telescopes like JWST analyze exoplanet atmospheres for biosignatures, gases like oxygen or methane that could betray the presence of biology. A single whiff of these molecules on a distant world would tilt the scales dramatically, suggesting the universe is indeed fertile ground for life, which brings us to the ultimate question: if life isn't unique to Earth, where is everyone? The search for extraterrestrial intelligence SETI has scanned the skies for artificial signals for over 60 years, so far in silence, but new approaches are breathing life into the hunt. Breakthrough Listen analyzes millions of radio channels simultaneously, while technosignature searches look for Dyson spheres or industrial pollution in exoplanet atmospheres. Even the absence of a detection is meaningful. It might suggest that intelligent life is exceptionally rare, or that civilizations tend to self-destruct before achieving interstellar communication. Or perhaps we're simply not listening the right way, like using a telegraph in the age of fiber optics. What's clear is that we're no longer guessing about our place in the cosmos. With every new exoplanet discovered, we gather more pieces of a puzzle that stretches back to the Big Bang itself. The universe spent billions of years forging heavy elements in stellar furnaces, scattering them across galaxies to form new stars and planets. Now, on at least one small world, those atoms have begun to contemplate their own origins. Whether we're alone or part of a vast cosmic community, the very act of searching connects us to something profound, a universe that may have always been destined to wake up and look back at itself. For over 60 years, humanity has trained radio telescopes on the stars, listening for whispers of intelligence beyond our solar system. Projects like SETI, the search for extraterrestrial intelligence, have scanned millions of frequencies, hunting for patterns that betray the handiwork of another civilization. Yet the cosmos remains eerily silent. This silence sits at the heart of the Fermi paradox, a question that grows more perplexing with every exoplanet discovered. If the universe is so vast and ancient, why haven't we found any trace of other technological life? The numbers alone suggest we should be drowning in evidence. With hundreds of billions of stars in our galaxy, many older than the Sun, and trillions of galaxies beyond, the statistical odds seem overwhelmingly in favor of cosmic company. So where is everybody? One chilling answer lies in the concept of the Great Filter, a hypothetical barrier that prevents life from progressing to interstellar communication. This filter could lurk in our past, meaning the emergence of complex life is so astronomically unlikely that Earth is a fluke. Perhaps the leap from single-celled organisms to multicellular life requires such precise conditions that it's only happened once. Or the filter might await us in the future, a catastrophic bottleneck like nuclear war, runaway AI, or ecological collapse that civilizations inevitably stumble into. The unsettling truth is that if the filter is ahead of us, humanity's long-term survival prospects could be grim. Every silent star system becomes a warning sign, a graveyard of civilizations that failed to navigate the same perilous path we're now on. But not all explanations are so dire. Alternative solutions to the Fermi paradox stretch the imagination in other ways. Maybe advanced civilizations exist, but they've transitioned to forms we can't recognize, uploading their minds into quantum computers or harnessing dark matter in ways invisible to our instruments. Others propose a galactic zoo hypothesis, where alien societies deliberately avoid contact to let us develop undisturbed, like anthropologists observing an uncontacted tribe. There's even the possibility that interstellar travel is far harder than we assume, constrained by physics or energy requirements that make galactic empires impractical. The stakes of this search couldn't be higher. Initiatives like Breakthrough Listen, with its unprecedented access to radio telescopes like Green Bank and Parkes, are scanning the million stars closest to Earth with sensitivity that could detect a radar signal from dozens of light years away. Meanwhile, technosignature hunts look for industrial pollutants in exoplanet atmospheres or the infrared glow of Dyson spheres, hypothetical megastructures built to harness a star's energy. A single confirmed signal would shatter our cosmic isolation, proving we're not alone in the universe's grand story. The psychological and philosophical impact would be seismic, reshaping everything from religion to geopolitics. Would humanity unite in the face of a shared cosmic identity, or would old divisions persist even among the stars? Perhaps the most profound lesson of SETI silence isn't about aliens at all, it's about us. The universe's quiet might be urging us to mature, to recognize that intelligence is fragile and precious. If civilizations are rare, then every spark of consciousness is a marvel to be protected. Or perhaps the answer is simpler, we're just early. The universe is 13.8 billion years old, but it could endure for trillions more, enough time for countless civilizations to rise long after we're gone. Either way, the act of listening itself is transformative. By straining to hear voices in the cosmic dark, we're forced to confront our own place in the vastness, not as the universe's protagonists, but as fleeting participants in a story far greater than ourselves. Carl Sagan's Cosmos didn't just teach science, it turned the Big Bang into a cultural touchstone. When the series premiered in 1980, Sagan's poetic narration and the show's psychedelic visualizations, like the cosmic calendar, compressing billions of years into 12 months, made abstract cosmology feel intimate. For millions, this was their first glimpse of the universe's origin story, not as a dry equation, but as a sweeping epic where they played a part. Sagan's genius lay in framing the Big Bang not just as physics, but as mythology for the modern age. His iconic phrase, "We are made of star stuff," bridged the lab and the living room, transforming nucleosynthesis into a shared human heritage. Hollywood, however, took liberties. Blockbusters like Star Trek and Doctor Who often depicted the Big Bang as a literal explosion, a fiery burst in empty space. This visual shorthand is understandable, but it's also misleading. The Big Bang wasn't an eruption into space. It was the rapid expansion of space itself, a nuance even some textbooks struggle to convey. Films like The Tree of Life leaned into abstraction, using swirling nebulae and Terrence Malick's existential voiceovers to evoke the singularity's mystery. While scientifically loose, these portrayals captured something equations alone can't: the existential awe of cosmic birth. Then came The Big Bang Theory, the sitcom that turned astrophysicists into primetime stars. While the show's laugh tracks and geek stereotypes drew mixed reactions from scientists, its cultural impact was undeniable. Overnight, terms like singularity and dark matter entered coffee break conversations. The writers even consulted Nobel laureates to ensure whiteboard equations were accurate, though Sheldon's Bazinga moments often overshadowed the science. Love it or hate it, the show made cosmology feel approachable, proving even quark-gluon plasma could be punchline material. Beyond screens, artists like composer John Adams, Dr. Atomic, and painter Julie Mehretu The Big Bang and the Dark Universe translated cosmic violence into symphonies and brushstrokes. Their work asks a daring question: what if science and art aren't opposites but two languages describing the same wonder? When the Large Hadron Collider launched, it inspired a CERN artist residency, where creators danced with data visualizations and turned particle collisions into poetry. This cultural dialogue matters because it shapes how society values science. A child watching Cosmos might become an astronomer. A Big Bang Theory gag could spark a late-night Wikipedia dive. Misconceptions persist, yes, but the bigger truth is this. The story of the universe is too grand to stay locked in journals. It belongs to poets, filmmakers, and curious minds everywhere, each retelling adding new color to the cosmos' oldest tale. And as we stand on the shoulders of these storytellers, we're reminded that understanding the Big Bang isn't just about tracing particles. It's about seeing our place in a narrative 13.8 billion